Today we will talk a bit about this message passing neural quantum state paper, we call it MP-NQS paper by Giuseppe Kallio's group. Uh, so we'll see that it compares very favorably compared with Ferminet and also DNC and also another architecture WebNet, which I've not had the chance to look at. But anyway, but it's a rather interesting architecture. Okay, there we go. Okay, so let's just talk a little bit about the physics background of this thing. So the main physics idea or the main physics motivation for this is iterative backflow transformation. It's basically the way they conceive of this backflow coordinates is to carry out an imaginary time evolution of an initial state phi naught. Then you apply the thermal density operator e to the tau h minus tau h to it, and then you take the x or k position representation or whatever you like, and this will be phi tau. So basically, it's the imaginary time evolution of some initial state. So the key point here is that phi naught has to have some non-zero overlap with the final ground state. So it has to be non-orthogonal. Sorry. So the symmetries and of the system of the phi naught has to be the same as the symmetries of the final state. Okay, and and then when we take tau going to infinity, then we'll see that you will naturally evolve to the ground state of the system. So this is basically the main idea behind DNC, and then we are applying it to a neural network right now. So how do you get phi tau of x? Phi tau of x is actually you insert a complete set of states x prime, and then you can see that you can be written in terms of this Green's function operator. This Green's function operator is actually the many-body exact solution of the many-body Schrodinger's equation. So this is not the two-point correlation function, but rather the full Green's function for the full many-body system. So you integrate g of x prime over phi naught of x prime, and then you'll get, oh, there's a subscript tau. Sorry, I missed it out. Anyway, and then you get phi tau of x, and then you let tau go to infinity, and that's what you get. And then the way then one simple way of solving this is to use a mean value theorem. So you assume that omega is some convex domain, and then over a convex domain, you can always find the center of mass of the integrand, and then this is how you get a generalized backflow coordinate. The backflow coordinate y of x is basically the center of mass coordinate for this that gives you the mean value solution of this integral, and then our entire problem simplifies to finding these backflow coordinates y of x, basically some special transformation from x to y.
I have a quick question about that slide.
Uh-huh.
So just to clarify, by mean value points, you mean like the x prime for which g of x comma x prime is maximized, right?
No. It's the center of mass value of this integrand. It's basically if you
What does that mean, center of mass? Yeah, I don't understand.
It's so if you carry out this integral g of x prime phi naught of x prime, it will give you a finite value over the domain omega, and then you can represent this value by some I guess centroid value for x prime in terms of y. That's what it means. But how to get this y of x to represent? So basically, this entire thing, g of x of y times phi naught of y, has to be exactly equal to this integral gx x prime of phi naught of x prime. That's the mean value theorem.
Yeah, I don't quite understand what. equal
Wait, do you mean just you're imposing like the right hand side of the second line is equal to right hand side of the third line, and
Yeah,
in
that's
that way
right.
you
Yeah,
apply?
yeah.
it's a bit unclear. Yeah. Anyway, why don't you go ahead first? Yeah.
Wait, sorry, can I ask just one more quick thing? Sorry. So like for like let's say like n particles, like the uniform electron gas, I think it's
Mm-hmm.
known that if you don't explicitly enforce the particle statistics, then the ground state is a bosonic wave function. So that's why you can't do diffusion Monte Carlo for fermionic systems without a trial wave function. So is that like a problem here, or
Wait. If you do not impose the fermionic statistics, you end up with a bosonic wave function. Yeah, okay. But you have to enforce the fermionic statistics, right?
okay? Well, yeah. So what I was referring to is that, and it's known that in diffusion Monte Carlo, even if you start out with with a perfectly anti-symmetric wave function, like the
Mm-hmm.
accumulation of numerical error as you apply e to the minus tau h eventually
Mm-hmm.
takes you to like a bosonic state, because the bosonic state is lower. It's probably fine. Yeah, never mind.
Okay,
Yeah, whatever.
I'm not that familiar with the diffusion Monte Carlo, but okay. Um, but okay, just based on, because this is okay. So just based on the paper, this is their physical motivation, and I guess maybe we can get into the DNC a bit more later on in other talks. So which is not okay. So so the symmetry constraints of the wave function tell us that we have to be anti-symmetric, but g of x prime is symmetric under exchange. So this gives us some constraints on constructing the neural network for the backflow coordinates. So g of x prime has to be symmetric under exchange. So if you exchange particles ij for x and x prime, then they are is symmetric to g of x prime. So basically, what that means is the backflow coordinates are equivariant. If you apply this particle exchange Pij on x prime, then the backflow coordinate that you get for y has to be equivalent to applying the particle exchange on the y on the backflow coordinate that you get from x itself. So the neural network that we have to construct is equivariant, and that's what attention mechanism does. then then so the neural network ansatz at the end of the day will be a symmetric function g of x of y times an anti-symmetric function phi naught of y. And so the anti-symmetric part can be represented by a determinant, and then the symmetric part is an overall factor. It turns out to be an exponential of a Jastrow factor, of a neural network Jastrow factor, which you can absorb into the orbitals phi of mu. So this is what they use to construct the neural network later on. Okay, so so what's MP-NQS? MP-NQS is basically an all-to-all connected graph neural network. So a graph neural network consists of particles or nodes or vertices and interactions, which are edges. And then we have a set of vectors that describe the information or the features that we want to encode at each position or each vertex, and as well as at each edge. So we denote them by Gi at layer n. N refers to which GNN layer we are at. And then we also have a Gij for each interaction edge. And then in this MP-NQS construction, Gi and Gij are concatenations, or basically lumping together of Xi naught and Hi. So Xi naught are some initial feature vectors that we keep throughout all the different layers. So Xi naught in machine language terminology is known as a skip connection. So the purpose of keeping Xi naught the same for each layer is to mitigate the barren plateau or the vanishing gradient problem. So that's something that is sort of a standard trick in machine learning community. And then same thing for the edges. We we construct some hidden features, some initial features, as well as some hidden features. And then the hidden features will be updated from layer to layer. And then the main crux of MP-NQS is this message passing update.
Xij is the distance between particles, the xi minus x.
Yes. Basically, later on, it'll be some periodic version of the
particle. Okay, fine, that's fine.
Yeah. And then Hi and Hij will be some machine learned feature vectors. Okay. So the main thing, I think the main crux of the paper is this attention mechanism for the message passing update, which they call particle attention, and then we'll describe that in more detail later. Okay, so just to
can I have one question? Like, because I think in Ferminet they don't really use like the original coordinates for each layer. So like as you mentioned, like you can solve like the vanishing gradient problem. So you mean basically you feed this same coordinates thing into every single layer alongside Hij. Is that what you mean?
wait, sorry, can you repeat that? I didn't quite. So in Ferminet, they don't use
Yeah, I
Xij.
don't think.
Okay.
Yeah. I think they just each layer is just Ji from
Previous layer.
construct last layer. Yeah.
So it's
exactly.
basically a bunch of feature vectors that they feed from layer to layer, right?
So basically, this should be like theoretically better than Ferminet then, like architecture wise.
Yes, it performs better in terms of both the energy and the number of parameters, and also the convergence rate.
Okay, sounds good. Thanks.
Yeah, I mean, this is the reason why I suggest this paper, because in all the recent work that D and I have been doing, we're using this framework, message passing. Yeah, from this paper on electron hole bilayer, also with David, we've been using this message passing thing. So that's why I thought, and D told me that with all these new generations, it requires far less parameters. So that's why I thought this would be a useful thing. Yeah. But on the other hand, you have great success already with Ferminet. So I'm happy.
Anyway,
I know our group, we just want to get a sense first about what is the current state of art, right? And then when we explore various applications, we can just pick up whatever is convenient. If we already have great success with Ferminet, we'll still stay with it, right? But on the other hand, we can also explore a little bit. But
I feel like adding this wouldn't be like extremely hard. I mean, it's just adding one feature to each layer. But yeah,
no. I mean, the thing is, this code is also online, right? This code is also online. Yeah.
Okay, yeah.
We're exploring different things. Yeah.
Okay.
Go ahead.
Is there an assumption on what kind of entanglement between particles you take? So basically, I'm thinking is like the state describable only by single particle and two particle density matrices, because you only take vertices and interactions.
No. This is universal theorem that all these neural network can in principle represent any many wave functions besides x.
So I guess just to clarify, sorry, you go ahead. Sorry.
No, that's all I want to say. That there is yeah.
But I think that's a good point. Was that Max? So the what MP-NQS does is it constructs a GNN for updating the backflow coordinates Y, and then after that it uses a final layer W to convert all these GIs and GIJs into a backflow coordinate. They call it delta of R here, and then sorry. Oh. And then and then they feed it into a bunch of this single particle orbitals and construct a single slated determinant out of it. But yeah, but maybe thinking about neural network constructs in terms of 1, 2, and maybe even 3, 4 particle reduced density matrices may be helpful, but they're working with more this first quantized picture right now.
I see. Yeah, thank you.
Yeah. So yeah, so basically, this MP-NQS in some sense it focuses on constructing the backflow coordinates first, and not on the wave function. Okay, so yeah. So okay, so just a brief overview of what GNN is. GNN is has basically consists of nodes, these yellow colored things, edges, the blue ones, and then also in some architecture you have a global master node, this pink thing, and then you have UN, which is the feature vector associated with the master node, VN, which is the features associated with the vertices, and then EN, which are the feature vectors associated with the edges.
Let me just understand, like in terms of language, right? So last time Karen gave this beautiful talk, and as she explained, like in neural networks, right, you have neurons. Each layer consists of neurons, and neurons receive some sort of inputs, right? Bias and weights, right? That's a language that people use, right? I think bias are more like the input from the previous layer. That's the idea, Karen.
Or that was activations.
Activation,
is
sorry,
what you
activation.
compute. And
Activation
each
is
node,
is
yeah.
received from the previous layer, and then the bias is what? Yeah, bias is something that you add some constants, right? Add some
Yes,
constants,
yes, and then you
and then there's
multiply by the weights.
There's a weights, yeah. So now, I guess for GNN, right, you're trying to describe the corresponding thing, right, in GNN, right? So, are there neurons?
Yeah. For at the first layer or the nth layer, we have UN, VN, and EN, which are the information associated with all these vertices, edges, and nodes. So the most straightforward way to construct multiple layers of GNN, so you go from layer n to n+1, is you feed all these UN, VN, and EN into a neural network or machine. Yeah, and then you have all your weights, biases, and stuff like that. And then, yeah.
So I should think of each layer as like basically representing a particle configuration, right?
Yeah.
Right.
You can think of it.
Updating from one particle configuration to another particle configuration, right?
Yeah.
Okay.
Yeah.
All right.
And then
then, from one layer to the next layer, they undergo this neural network, one layer of neural network process. You are saying U, V, and E are fitted into this thing F, right?
Yeah, that's right.
All right, sounds good.
So this is the.
So can I think that basically you're representing the in the case of the usual you're representing, in other words you're trying to changing the basically, okay, in the case of what Karen described, that you have each layer outputs some activation to the next layer, right? You can think of activation as a set of it's a vector, right? The whole
Right.
And here it generates a vector into a graph. Can I think of that? The generalization from the vector of a vector that contains all the activations. It changes that into turn that into a graph. It's more richer structure.
Yeah, that's right. Yeah.
Yeah. All right.
Wait, can I ask one question? So like in each layer, you also have like different links, right? So because does that mean like you construct like the layer feature from different neurons, from information of different neurons in each layer, and then you feed them into the next one? Because I mean the most straightforward.
Sorry, what do you mean different lengths? You mean the
No,
length
different lengths. It's like if you're just describing like the simplest neural network, for example, the one, for example, like the Fermi-net, it would just be like, let's say in each layer, I don't think you would have different links. Like you will link between one layer to the next, like whatever connectivity. I mean, maybe all to all, maybe not all to all, but like I think in your graph, like in layer n and in layer n+1 itself, it also has different.
Okay.
So what does that actually mean?
So in neural, okay, so it's like, okay, let me just recall. In FermiNet, you have but each layer is a new each layer is basically an MLP or neural network layer, and then you have cross connections between in each layer as well as cross connections from layer to layer. Okay, and sorry, and then okay, and then your question here is, do we do the same thing?
I mean, I just don't know exactly, for example, this shape in your layer, and what does that mean? Like,
Layer, you mean the
because
subscript?
like the concatenation you talk about is from one layer to another, right?
No. The concatenation here. You mean the concatenation here? This one?
Oh, so it's from one layer to itself.
Yes, to itself. It's the concatenation is
Oh
I
yeah, that's
construct.
fine. I mean,
Yeah.
oh, okay, that's the link. Okay, that's fine.
I
got it. Yeah.
construct some initial feature vectors, and then I keep them unchanged. I keep them the same for all the layers, and then by the same time I construct a bunch of hidden vectors H that are updated layer by layer.
So like the cross-layer communications from layer n to n+1, what you're communicating is GI and GIJ, right?
Yes, you use GI and GIJ to update GI and GIJ of n+1.
Yeah, okay, yeah.
Okay.
Wait, but the next layer you also have you also have xi0 and hi n+1, right? So you have two
Yeah.
ways to construct GI plus n+1. One is from x and h, one is from the previous g, right?
Xi doesn't change. Xi is the same for all the layers. What changes is HI. Xi doesn't change. HI
So
changes.
ultimately you're communicating via hi, but not GI
Yes.
then. Oh, okay.
No, you
Yeah.
use GI to construct the messages that are used to update HI.
How do you update hi from GI?
Okay, maybe a couple of slides later on we'll see.
Oh, okay, yeah.
A little bit easier
All
with,
right.
with the equations
Yeah,
and
yeah. All right, thanks.
no, it's okay. Yeah, thanks, Tony. Just just maybe 2 steps ahead of everyone else. So this is the simplest way. You have these neural networks for different neural networks for each one for UN, VN, and EN. But you're not really making use of the connectivity of the graph here. I mean, the vertices. This one I depends on all the other nodes. Let's say call this 1. It depends on 2, 3, and 4. And then, so it also depends on the interactions between 1 and 2, 1 and 3, 1 and 4, 1 and 5. So in order to make use of the richer set of information, what you do is you pull information together. So for example, okay, let's say I want to look at the vertex I here. And then I pull all the information from the vertices that are connected, from all the edges that are connected to it. So I sum over ij, all the nearest ijs. So I sum over, 1 to 2, 1 to 3, 1 to 4, 1 to 5, but I don't sum over h2 and 3, h4 and 5, because they're not directly connected to 1. So so I get this pooled or this lumped set of information rho I, and then I feed it into another neural network C, and then I use this this lumped set of information to update VI of n+1. So that's called pooling information. Okay. Now then, so message passing. So message passing is in some sense a generalization of this pooling of information. So okay. So I I construct I lump together all the information. So for let's say vertex I lump together information. I of course use VI itself, then VJ, which are the nearest neighbors, and also EIJ, which are the ones that are connected to I, the nearest neighbor interactions. And then I feed it into another neural network, and then this will be the message that is used to update the next the vertex for the next layer. Okay, so this is message passing for the vertex. Then same thing, message passing for the edges will be VI and VJ.
You probably won't be able to follow the details. Like, what is the big picture?
A big picture is basically you want to you want to the big picture
Let me ask
is
you this way. Compared to the structure, the architecture that Karen talked about, right? You start feeding activations and with bias and weights, etc. Passing it from layer to layer. What is the advantage of this message?
the
what is the
advantage of
advantage of using vertex, edge, and what is the other thing? Yeah.
the vertex and the edge. So the vertex, you can think of it as like the information of each particle, and then the edges will encode the interaction, the different types of interaction between the particles, and then so the simple way to think of it is that this most architecture here use capture the information from your nearest neighbor interaction. And then when you go from layer 1 to layer 2, you capture the nearest neighbor interaction and the nearest neighbor information. And then when you go from to the third layer, then you capture the next nearest neighbor information.
Okay.
So the message sort of starts to spread out to your first nearest neighbor. Yeah.
Okay, sounds good. Okay, yeah. Continue. Yeah, the details we probably cannot follow right now, but maybe we can give some.
Okay, sure. But the basic idea is the message starts to spread out.
Okay.
Yeah.
Continue. Yeah.
Okay. So okay, then now, like I was saying, the message passing is constructed from attention mechanism. So like I was saying, the backflow coordinates has to be this equivariant under permutation. So in neural networks, a permutation equivariant architecture is a self-attention mechanism. So so basically, so it's called a QK transpose V or QKV method. So the basic idea is it sort of came from large language models. So let's say you want to look at how similar words are, and so the word will be your input feature, your input vector, and then you use your input feature, this OIR or O1, O2, O3, whatever, to construct your keys. Then your keys will be basically some encoding of the different words, and then the query basically tells you it's like how similar different words are. So it's an overlap or a covariance matrix of Q and K. And because it's a covariance matrix, and you take QK transpose, so when you permute I to J, it permutes the rows of Q and it permutes the columns of K. So this thing becomes permutation invariant. And you also permute Vij. So the whole thing that you ends up being permutation equivariant. So when you change from I to J on the input features, you also change from I to J on the output messages. So that's the basic idea. So that's what self-attention is. You use some input values to construct some mathematical encoding that helps to capture the key features of the different words. And then when you feed in different queries, then you see the ones that are closest to the key values will be highlighted. The ones that are not as close to the key values of the encoded words, they will have less weight, and then you output to some value V. So that's basically attention mechanism in a nutshell. Okay.
Can you elaborate a bit on it? Are there any, like, let's say, some like physical meaning of QK and V, maybe?
Okay, why don't we just the next slide we'll talk about MP-NQS, and then yeah, we'll just okay. So GIJ, okay. So GIJ are the main crux of MP-NQS is this attention mechanism for the interaction or the edges between the particles, and then these interaction features are encoded in GIJ. Okay, so there is some matrix WK and WQ that transforms these GIJs into some optimal linear superposition. So basically, let's say GIJ is let's say this edge here 1 to 2, and then it has a bunch of different features. And then what you do is you take WK as which is a matrix to transform all these features into some optimal, maybe like a PCA or more orthogonal set of vectors to describe the interaction between 1 and 2. And then and then you want to, and then when you query this thing, you use you construct this QIJ. So the message that is constructed is, okay, so it'll be so the message that is constructed is constructed from Q times K, but you sum over all the L, basically all the nearest, all the connecting neighbors. So let's say this is 1 and 2. So Q, let's say omega ij is this omega 1, 2, and then QIL will be Q 1 to 3, and then K 3 to 2. So basically, all the information, so the updated information or the new effective interaction between 1 and 2 includes information from 1 to 3 and then 3 to 2. So that's the physics behind it.
Wow. So is that like renormalization then basically? You're like
it'd be nice to, I don't know, it'd be nice to maybe think about it along yeah, it'd be nice to think along those lines. We could talk more about it, but I think it's more like, yeah, maybe it's
but that only takes care of like the next nearest neighbor, right? So it's like real space renormalization, right? Like
a bit. But then when you go, but then this is from layer 1 to layer 2, and then when you go to layer 3, you include the next nearest neighbor interactions.
Oh, okay.
So you have you also, so successive layers will give you more and more information about effective interactions coming from further and further neighbors.
I see. Wait,
Yeah.
so each layer, I feel like it seems each layer is almost like a neural network itself, like because I mean, because already in each layer you're feeding information among different points, like which you normally then, I guess.
That's the point of a GNN. You make use of the connections between the different particles or the different vertices to have a more complete description of that of the system at each. Yeah.
Thanks.
So okay, so omega ij. So well, to be technical, the message is actually constructed by omega ij, which is this bunch of feature vectors multiplied by well, first they feed gij into a machine into another neural network to do some matrix, to do some linear transformation, and then you end up with a vector of this length feature, and then you construct this thing omega ij, which is also a vector of the same feature dimension length, and then they do element-wise or bitwise multiplication, and then basically and then this is what, and then you end up getting a message mij, which is a vector of length dimension for each edge, and then this one is, in some sense, you think of it as the effective interaction for between I and J, and then when you the way you update your next vertex for the next layer is you sum over all the messages that are connected to this vertex, and then the edges are just updated by this effective interaction from that edge itself. So that's MP-NQS. This is the attention part of MP-NQS. Okay. The important thing is that these WK and WQs, they do not depend on the particle. So they do not change when you increase the number of particles in the system. So this allows them to keep the parameter size small. And then later on we'll see that's a reason why it's this MP-NQS is fast and efficient. So basically the thing is, note here that WK and WQ has no IJ index on them. All the IJ information comes from the hidden vectors or the state vectors. Okay, and then after you do all, go through a bunch of GNN layers, and then when you get to the last one, GI or big N, and then you construct your backflow coordinate from some final neural network that multiplies these GI or final state vectors, and then you get your final backflow coordinate, and then this is what they use to construct the machine learning or machine learned Jastrow factor. They do some again here small j is some neural network transformation, and then you feed, and then you put it into a Jastrow form or exponential form, without putting, and then the final result is that you are able to learn the cusp of the wave functions from these backflow coordinates. Okay, here again, Liang had some questions about how you construct xi and xi, xi and xij. These are just, so you just make sure that they are spin and translationally invariant. So you transform them into into sine and cosine, and then because it's a spin inversion symmetric, so you cannot label up and down. You can only label si.sj.
Mm-hmm. Very
Yeah.
good.
So that's
Yeah.
and then and then in the Fermi liquid state or at small rs, you use plane waves, and then at large rs they use Gaussian orbitals.
Wait. They're changing the ansatz.
They changed the form of the single particle
Ansatz?
orbitals.
Really? Oh, that's cheating. Yeah, that's really cheating. No, that's something very, very cheating. Yeah. But
Well, I mean,
our
like,
paper with the D, with this, well, we can chat more about this offline. Yeah. So we have
okay,
a architecture.
that's what they did. They basically they chose a bunch of Gaussian orbitals localized on the BCC sites. Basically, you already sort of you pre-know or
Yeah, but
presuppose.
that's cheating. That's really cheating. That's not good. No.
Okay,
I think the original Fermi-Net paper, when they discovered the Fermi liquid to Wigner crystal transition, they're not feeding this information by hand.
okay.
Is that right? I mean, Tony? Yeah.
Yeah, I mean they just realized that they can actually do pretty well without any pre-training. So
Yeah, without any pre-training, they did it. Yeah. So this is cheating. Yeah. This MP-NQS, this is really cheating, I think. Because how do you know, for a given parameter, right? For let's say RS equal 20, should I use a Fermi liquid or should I use a Wigner crystal like ansatz?
Yeah. Well, we can look at their detailed results later. I think they get reasonable. I think they are. We'll take a look later. They do it. I think they are actually they are. I think they are they're not cheating too much. When at some RS values, but I'll show you the. Okay. So some of the key features of MP-NQS. It's MP-NQS, like I was saying. It's because WK and WQ do not depend on the particle index ij, so you can reduce the number of network parameters.
wait, but I'm like really surprised by. I mean, I understand the fact that the number of parameters are less, but that basically means that your architecture has to be much more efficient, right? Because it doesn't guarantee that when you just reduce the input information that you will still get like a same expressive power or something.
Yes, that's something that the expressivity of the they did not explicitly discuss that. I think we can talk a bit more about that. But anyway, let me just state what their claim is. So again, like like I was explaining earlier, when you go from as you go from GNN layer 1 to 2 to 3, they slowly capture more and more of the effective interactions from nearest and next nearest neighbors. So they claim that this allows them to capture all the additional correlations, and then by putting it into the backflow coordinates, and then with an appropriate neural network transformation, they are able to capture the Jastrow factor and the cusp properly.
Mhm.
So So numerically, what they they back it up by showing that they use only 20,000 parameters as compared to about 1 million parameters for Ferminet, which uses 32 slated determinants, and then they only use 1 slated determinant. And then Ferminet, they claim needs about 100,000 epochs or cycles to converge, but they only need about 1,000 cycles to converge. So both in terms of convergence and number of parameters, they have an 2 orders of magnitude improvement. And because they only have 20,000 parameters as compared to a million parameters, they can use stochastic reconfiguration, or they can basically calculate the Fisher information metric of the variational wave function and update very well or very quickly. So I guess that's why they can converge much faster compared to Ferminet.
Wait, but Ferminet also calculated the Fisher. Oh, you mean just calculate exactly without any? Without.
They calculate the what they call the preconditional matrix, which is which is equal to the Fisher information. Whereas you have to do K-fact and whatever stuff in Ferminet.
Yeah, that's fine. Yeah, I see. Nice.
Yeah. So okay. So in terms of their results, they okay. So zero. Sorry. Is there a question?
I mean, you were close to wrap up. Is this
Yeah.
close to-
Yeah.
Okay.
So zero is MP-NQS value, the ground state energy, and at small RS, you can see that Ferminet is a bit better, but at large RS, they beat Ferminet and also WebNet, which is another architecture. And then at RS equals to fifth, this is for 14, and then for 54 electrons, they compare with DMC, and then they show that they are better than DMC as well. And then so and then the yellow one is the Gaussian basis for MP-NQS, and so I think so they try to be somewhat honest here, I guess. They showed both the plane wave and the Gaussian basis results. And
Which one is the plane wave?
Plane wave is zero. Plane wave is they take plane wave to be their baseline, which is zero, and then compare everything else with respect to plane wave.
Yeah.
So and then they show that they have very close convergence compared with full CI for 14 electrons, and then for 54 electrons they compare with full CI as well as DMC results. So it's not bad.
Okay, sounds good.
Yeah. So that's it.
That's it. Okay, wonderful. Questions? Yeah, I do want to. I mean, we can chat. You and Junze, yeah, I can stay online later. I want to talk to you guys about some concrete project. Yeah, but to understand correctly, you guys can get this running now.
Yeah, Junze got it running, and then also we also install Ferminet as well, and then that's Howren managed to install Ferminet as well.
Oh, great! Because I saw Tony wanted to be able to install it on the.
No, I mean, I was able to install it, but have you guys already managed to use GPU to run it?
Junze, Howren, you guys want to?
Yeah, Junze, feel free to. Yeah.
Yeah,